Hello, in this class we will discuss electrical properties of colloids and generation of charge, that is origin of charge in the colloidal particles, then electrical double layered Zeta potential, electrophoresis, electro-osmosis and related problems. Charge on colloidal particles and their stability. So stability of colloidal particles, it has some relationship with the charge. So let's see what is the relationship. Colloidal particles possess a definite type of electrical charge. It may be positive, it may be negative. Now, all the colloidal particles, it will carry the similar type of charge. So here we have one particle, this is another particle, you can see it is carrying positive charge. Now when we are talking about dispersion medium, this is dispersion medium. In the dispersion medium, there will be equal but opposite charge. So here we have negative charge because positive charge is present on the colloidal particles. So as we have equal and opposite charge, so the charge on the colloidal particles, ultimately it will be balanced. That is, it will be electrically neutral as a whole, because in the dispersion medium there is opposite charge, and it will be vice versa. That is, negative charge on colloidal particle, now there will be positive charge in the dispersion medium. The presence of this type of equal and similar charges on colloidal particles, that is actually responsible in providing stability to the colloidal particles. So because of this similar type of charges, there will be repulsion between the colloidal particles, and as a result they will not be able to come close to each other. So aggregation is not possible, and when aggregation is not possible, large particle formation will not take place, and as a result there will be no precipitation, so it will be stable. That is, the colloid will attain stability. So in this way, charge is responsible for the stability of colloids. Now we will see some examples of negatively charged colloids and positively charged colloids. Positively charged salts, hydrated metallic oxides, that is Al2O3xH2O, CrO3xH2O. We can see in all these three examples there is water molecules attached. So when we have this type of metallic oxides, that is hydrated, they will be positively charged. Then basic disturbs, for example methylene blue salt, hemoglobin present in blood, and TiO2 oxide, metallic oxide. And negatively charged salt, simple metals, copper, silver, gold salt, metallic sulfides, that is arsenic sulfide, antimony sulfide, cadmium sulfide. Acid disturb, in this case we have seen basic disturb, positively charged colloid, but negatively charged colloid, it will be acid disturb. Example eosine, Congo red salts, etc. And salts of starch, gum, gelatin, clay, charcoal, all these are also negatively charged salts. So it is better if you can remember some of these examples, because sometimes in the question it will be mentioned, some of these salts may be mentioned. So if you do not know what is the charge present on this type of colloids, that is whether it is positively charged or negatively charged, maybe the related problems you will not be able to answer. Okay, so that is why it is important to remember the charge of this, that is what is the nature of the charge present on the salt. And while we will discuss the problem, it will be clear why it is important for us to memorize, that is at least some examples, whether there is a positive charge present on the surface or negative charge is present on the surface of colloidal particles. Okay. Origin of charge on colloidal particles. Now, charge is present on the surface of colloidal particles, that we have already seen, but how it is generated, that we have to know. So there are different ways by which charge may be originated on the colloidal particle surface. Here the first point we have dissociation of the adsorbed molecular electrolytes. Colloidal particles have a strong tendency to adsorb reactant or product molecules. Now that is, when colloidal particles are formed, there is some static material, that is reactant molecules, and there is also some product molecules. Now these colloidal particles, they will have a tendency to adsorb the reactant or product particles. That is, if there is some excess reactant present, and product molecules will always be there, so any of these molecules may be adsorbed. Now the molecules thus absorbed on the surface of the colloidal particles, if they are undergoing dissociation or ionization, they will be responsible for the charge on the surface of these colloidal particles. So for example, suppose we are preparing sulfide salts, arsenic sulfide. So to prepare arsenic sulfide, we have used the starting material H2S. Now if H2S molecules remaining, there is some amount of H2S, if it is present in excess amount, it will get absorbed on the colloidal particles. So AS2O3, it is actually negatively charged colloid that we have seen in the previous slide. So this is negatively charged, and H2S, that is the excess reagent that is present in the medium, if it is undergoing ionization, there will be formation of H plus and sulfide ion. Okay, now here H plus ions, they go into the medium. As a result, sulfide ions are left, which are present on this surface, and that is the reason that S2, S3, it is negatively charged colloid. Okay, so in this way H plus will be in the medium, but S2 minus, that will be remaining on the surface of the colloidal particles. So that is the reason H2S3 is negatively charged colloid. So this is the first way by which charge may be originated. The second possibility is dissociation of molecules forming colloidal aggregates. When we have discussed micelles, in that case we have seen how different, that is mostly long chain fatty acid molecules, sodium or potassium salt of long chain fatty acid molecules, they are aggregating together and making micelles. Now the formula, suppose it is RCOONA, sodium salt, and R is long chain of carbon and hydrogen. So these molecules, if they are dissociating to this anion and cation, now as it is dissociating, so RCO2 minus, that is where the long chain is present, when they will aggregate together to form the micelle, then it will carry negative charge, because negative charge is present. So the molecules responsible for the formation of aggregates of colloidal dimension, they themselves is now that is, they are undergoing dissociation, and as a result there is development of charge on the colloidal particles. So it is because of their aggregation. Okay, so several RCO2 minus anions, they will be together, and as a result there will be, suppose if it is micelle is like this, where the sphere portion is hydrophilic and the tail portion, that is hydrophobic. So here we have negative charge present because it is the polar head, that is CO2 minus. So in the surface there will be negative charge. The third possibility is preferential adsorption of ions from solution. Colloidal particles, they have a tendency to preferentially adsorb a particular type of ion from the solution. Now it will absorb those ions which are present in excess and also common to its own lattice. So we will take examples, then it will be clear. Now this preferential adsorption of a particular type of ion, it will impart a particular type of charge to colloidal particles. So if positively charged ions from the solution, now it is adsorbed on the colloidal particle surface, it will be positively charged colloidal particles, and vice versa. For example, suppose we have taken highly diluted AgNO3. So AgNO3 is present in excess, and we are adding to this slowly Ki, both are highly diluted. Okay, now there will be formation of AgI and KNO3. Now see, AgI, when it is AgNO3, that is before reaction, there is presence of Ag plus, after reaction also there is Ag plus. But I minus ion, if we consider, amount of I minus compared to Ag plus obviously less, because we are adding Ki slowly. AgNO3 present in excess, so Ag plus is excess, I minus is not excess. So if AgI is the colloidal particle, what are the ions present in it? Ag plus and I minus. So it will adsorb either Ag plus or I minus. But here Ag plus, it is present in excess and it is also common to its lattice. So that is why Ag plus will be adsorbed. So the precipitated AgI, it will absorb Ag plus ions from the dispersion medium, and as a result we will get positively charged colloidal sol. Okay, so here these conditions are maintained, that is which are present in excess and common to its lattice. So here Ag plus is present in excess and also it is common to the lattice of AgI. Another way is, that is the inverse addition. Now suppose you have taken Ki solution, that is in the container there is Ki solution present and we are adding AgNO3 slowly. So obviously in the medium there will be already K plus and I minus, and when we are adding AgNO3 slowly, now there is formation of AgI precipitate. But which ion is present in excess, Ag plus or I minus? It is I minus, because I minus is already associated with K plus, and AgNO3 we are adding dropwise or slowly. Okay, so that is why now I minus ion is excess, so that is why I minus ions will be absorbed on the surface of AgI particles from the dispersion medium, and as a result we will get negatively charged colloidal sol. Okay, so this is the picture for the second example. Here we have AgI sol and K plus I minus, as I minus is present in excess. So that is why now it is absorbed, and as a result we are getting negatively charged colloid. Okay, so these are the three ways by which charge may be originated on the colloidal particle surface. Now because of this type of charge, that is ion absorption on the surface of colloidal particles, electrical double layer will be formed. Now let's see what it means. Having acquired a positive or negative charge by selective adsorption on the surface of a colloidal particles, that we have already seen in the previous slides. So now the layer that is formed, this layer will attract counter ions from the medium and it will form a second layer. Okay, so already there is I minus, suppose if you consider the last example, so it will attract K plus, that is oppositely charged ion. Now the charge on colloidal particles, it will be balanced by an opposite charge. So I minus all this negative charge, that will be balanced by positive charge, and there will be a region around each colloidal particle where the charge on colloidal particle attracts the free ions for the dispersion medium. So this is the dispersion medium. Okay, and here free ions are present. So I minus, it will attract from these free ions the positive ions and vice versa. So this combination of two layers of opposite charge around the colloidal particle, it is called electrical double layer or Helmholtz electrical double layer. First layer of ions, it is firmly held and is termed as fixed layer. Okay, so this is the fixed layer you can see, and the next layer, it is also called Stern layer. Remember both these terms because any of these terms may be used. The second layer is mobile, so it is called as diffused layer. Okay, the first layer is tight, it is fixed in its position, but the second layer is diffused layer, so it will be in extended state, not like the first layer. And the boundary of the third layer, that will be called slipping plane or shear plane. Okay, though here we have mentioned only two layers, that is fixed layer and diffuse layer, but you can also consider third layer. And how it is, if you consider this surface area as the another layer, then there will be third layer. But just remember that after diffuse layer, that is a boundary of the diffuse layer, that is actually the slipping plane or shear plane. Okay, so whether it is third or second, that is not important, just remember it is the limit of diffuse layer, that is why the diffuse layer is ending, that plane is slipping plane or shear plane. Zeta potential. Now as when there is separation of charge, obviously some potential will be generated. So as we have separation of charge, separation of opposite charge in the electrical double layer, so obviously there will be generation of potential. Since separation of charge is a seat of potential, the charges of opposite signs on the fixed layer and the diffused layer of the double layer, it will be resulting difference in potential between these layers. Now the potential difference between this fixed layer and the diffused layer of the opposite charge, because these two are carrying opposite charge, that is called zeta potential or electromagnetic potential. So if you look at this picture, here this is the negative charge which is present in the colloidal particle surface, so we will call it negatively charged particle. Now as it is negatively charged particle, so there will be positively charged ions. Fine. So this is, if we draw a line, that is this surface, if we consider this is a surface potential. Now if we consider the next plane, that is Stern potential, and the last plane, that is the zeta potential. Okay, so just try to compare the picture and the graph. In the graph, in the y-axis we have potential, in the x-axis we have distance from the surface. As we are moving away from the surface area, then what will happen? Potential will decrease. So see, this is the closest distance to the surface, so here the corresponding potential is maximum. Then as you are moving towards right hand side, that is you are moving far away from surface, gradually the potential is decreasing. So just draw a point here. So this is the distance which is far from this surface, that is the starting point, and then consider this point. If you draw a line, this is also far from, that is further we are away from the surface. So as we are increasing in the value of distance from the surface, potential will decrease. So this is the nature of that is the relationship between the potential and the distance. As you are moving away from the surface, potential will decrease. Okay, so three types of potential, but the zeta potential, which is most important, it influences the effective size of the particle. Now size is very important, because depending on the size of the colloid, we can have different, that is it has direct impact on the properties. Now zeta potential also have impact on the effective size of the particle. That means zeta potential indirectly also controlling the properties of the colloid particles. Okay, so that is why it is very important. In presence of this double layer, the overall effect is that particles will repel each other when they are present at large distance of separation. As a result of this repulsion, they cannot come close to each other. And in absence of these double layers, what will happen? It will happen in presence of double layer. That is, there is repulsion, they cannot come too close to each other, they cannot form aggregated particles. As a result, there will be no precipitation. So it will be stable. But suppose if the double layer is not present, then what will happen? Then two particles of an insoluble material, they can come now close to each other, and attractive van der Waals forces, now it will be operative, it will pull them together. As a result, now they will be forming large particle, by that is they are combining with each other, particle size will increase. As a result, there will be precipitation. That means now the colloid is no longer stable. So that is the reason when we add excess of electrolyte, that will destroy the double layer, it will reduce the zeta potential, and ultimately colloid will be unstable and there will be precipitation. That is, colloid will be it will no longer be called as colloid. Okay, because dispersion medium and dispersion phase both will be separated from each other and there will be precipitation. Fine. Electrophoresis. So this is a property which is observed for colloidal particles. It is also related to their charge. Due to presence of particular type of electric charge that we have seen, it may be negative, it may be positive. So colloidal particles that are present in the dispersion, they will move towards a particular electrode when there is influence of electric field. So if the particle is positively charged, it will move towards cathode, If it is negatively charged, it will move towards anode. So the direction of movement of the colloidal particles, it is obviously dependent on the what type of charge is present on them, whether it is positive or negative. So these phenomena, that is, as they are moving towards cathode or anode depending on the charge, this phenomena is known as electrophoresis. And how we can define it? It may be defined as the movement of colloidal particles towards a particular electrode under the influence of an electric field. So here you can see, before electrophoresis, we have negatively charged particles of colloid, and here we have cathode and anode. So cathode and anode, as now that is when it is attached, what will happen? All the negatively charged particles, it will move towards anode. Okay, because here we have positive charge and this is negative charge. So basically in this way, dispersion phase, that will be separated from the dispersion medium. So you can say that it is also one type of precipitation of colloid, that is coagulation of colloid. Okay, so by electrophoresis we can, that is, destroy the stability of the colloidal particles. Now this phenomena, it has some applications. As here oppositely charged particles are moving towards cathode and anode depending on their charge, so obviously this by this process we will be able to detect what type of charge is present. Is it negative or is it positive? So if the particles are moving towards anode, that means it is negatively charged, and vice versa. So we can detect the type of charge. It is used in the removal of carbon particles from chimney gas. So in chimney gas, that means gaseous state, dispersion medium is gaseous state, and carbon particles, that is the solid state, which is dispersion medium. So solid in gaseous phase. So this is also a type of colloid. Now carbon particles, that is the particles of dispersion phase, if they are obviously they will move towards a particular electrode, and as a result we can remove carbon particles from chimney gases. Okay, that means basically we are separating dispersion phase from dispersion medium by the help of electrophoresis. And the third application, it is I have just said that it is used to bring about coagulation of salt. So here see, dispersion medium is present, but dispersion phase, that is here. That means now it is coagulated. Okay, so these are the applications of electrophoresis process. Next is electro-osmosis. Now we have already discussed osmosis in solutions chapter. Okay, but electro-osmosis, what is it? Here we will take the help of electric field, that is under the influence of electric field osmosis will take place. In the previous case we have seen particles of dispersion phase is moving towards electrode, but if the opposite thing is happening, that is if the particles of dispersion medium, they are moving towards the electrode. Now dispersion phase and dispersion medium both are actually carrying charge and they are opposite to each other. So if just consider the previous picture, here we have negatively charged dispersion phase. So if it is moving towards anode, because they are negatively charged, so obviously the dispersion medium, that is the particles that are present in dispersion medium, they will be positively charged and they will move towards cathode. So their direction will be opposite, because the particles of dispersion phase and dispersion medium both are opposite to each other. Now how it is possible? Under the influence of electric field, both will have a tendency to move towards oppositely charged electrodes. But how we can control the process so that only the particles of dispersion medium will be moving towards cathode? And that is possible if we use semi-permeable membrane. So it will not allow the passage of colloidal particles, that is the dispersion phase particles, but the particles of dispersion medium, it can pass through them because their size is lesser than the colloidal particles. So we can say that it is a dispersion medium that moves towards oppositely charged electrode. Fine, and this process is basically electro-osmosis. When the movement of colloidal particles under the influence of applied electric field is prevented with the help of suitable membrane, normally semi-permeable membrane is taken, then only the dispersion medium will move in the direction, and the direction obviously will be positive to the direction in which the colloidal particles would have otherwise moved if they are able to do so, but their movement is restricted because we have used semi-permeable membrane. Only the dispersion medium is moving, and this process is electro-osmosis. So you can say that it is a opposite inverse process of the electrophoresis process. Fine. Now we will see one problem regarding this. When an electric current, it is passed through the colloidal solution, and the experiment is arranged in such a way so that only dispersion medium will be moving. So this phenomena will be called, obviously it is electro-osmosis, because we have just discussed that when particles of dispersion medium is only moving, it is mentioned the experiment is so arranged. That means semi-permeable membrane is used. So that is why the colloidal particles cannot move, only dispersion medium can move. So this process is electro-osmosis. But if it is dispersion phase, that is colloidal particles, then it will be electrophoresis. But it is not electrophoresis. And what is electrolysis and electrodisintegration? Electrodisintegration, this is actually used for preparation of colloids, though we have not discussed it yet, but it will be discussed when it is under the preparation of colloids. And electrolysis is that we have seen in the chapter electrochemistry. It means that with the help of electrical energy we can perform some reaction which are under normal condition not spontaneous. Okay, so it is a conversion of electrical energy to chemical energy. That process is electrolysis. But here we are talking about colloidal particles, so obviously any of these two will be correct. But as it is the movement of dispersion medium, correct option will be option C. Next problem, we have to choose correct option. Only one of the four statements is true. Colloidal medicines are more effective because they have small surface area. The statement is correct up to this, that is colloidal medicines are more effective. Different medicines that are liquid in nature, you will see that their nature is colloidal. Okay, now it is true that colloidal medicines are used, but the reason that is mentioned in this statement, that is not correct. It is mentioned that they have small surface area, but actually it has large surface area if you compare with true solution. Okay, so when surface area is very high, medicines, it can be easily assimilated in the body. Okay, so that is the reason colloidal medicines are more effective. So the explanation that is up to this, it is correct, but the reason is not correct. So this statement as a whole is not correct. Second statement, addition of alum to water makes it unfit for drinking. Now the purpose of adding alum to water is basically to purify it. In water, if there is some presence of colloidal particles, when we are adding alum, it will act as electrolyte, so it will be helping in the precipitation of the salt particles. That means now the unwanted salt particles which are actually responsible for the impurity, that will be precipitated and we can filter it out. So that is the reason alum is used in water, and it makes water fit for drinking, not unfit for drinking. So this statement is also not correct. Third statement, colloidal particles in lyophobic salts can be precipitated by electrophoresis. Just remember in electrophoresis slide, in the application part of electrophoresis, there we have mentioned that this process can be used for precipitation, because under the electrical field influence, the movement, there will be movement of colloidal particles towards cathode or anode depending on the nature of their charge. So that means now the particles of dispersion phase, it is separated from dispersion medium. That means now the colloid is no longer stable, there will be precipitation. This statement is true. Option 3. And the last statement, Brownian motion in colloidal solution is faster if the viscosity of the solution is very high. Actually the reverse is true. Brownian motion, that is the movement of salt particles. Okay, now when it is faster, Obviously, when the viscosity is low, viscosity means what? It is the resistance towards the flow of the fluid. Okay, so viscosity high means resistance is very high. So if resistance is high, how Brownian motion, which is a mechanical property of colloidal solution, how it can be faster? It is not possible. So Brownian motion is faster when viscosity is low. So this statement is also not correct. Fine. Next one. Silver iodide, AgI, is used for producing artificial rains. Because AgI, basically we have to find which reason is correct. Easy to spray at high altitude, insoluble in water, has crystal structure similar to ice, easy to synthesize. Here correct option is option C. Silver iodide is used for producing artificial rains. Reason is it has crystal structure similar to ice. Now if it is so when AgI is sprayed over clouds where ice particles are present, okay, so what it will cause, as crystal structure is same, so the particles, they can be attached to each other. As a result, the size of the particle will increase. So the particle size, because of its increase, now it will be settling down because of gravity. So it causes water droplets of clouds to coalesce and it will form bigger water drops. Now the water drop size is bigger, so it will be precipitated, and that is also one rain. Okay, precipitation, here it is rain, so it will cause rain. So because of the same crystal structure, the particles can coalesce. So this is the actual explanation. Option C. Coagulation or precipitation. So we have already used this term, coagulation and precipitation. Both are actually same thing, but how we can, that is, what are the different methods we can, by which we can do coagulation or precipitation. Okay, but before that we have to understand what is coagulation specifically. Colloids, we know they are having some charge on their surface. So suppose if it is negatively charged, there will be repulsion between two particles. So presence of same type of charge on colloidal particles, it causes repulsion and it is actually responsible for their stability. Because if there is no repulsion, they will come close to each other, their size will increase, they will be precipitated. Now, if the charge of the colloidal particles is destroyed by some process, what are the process that we will be discussing? But right now just think, if this charge is destroyed, now they are able to come close to each other, their size will increase, and when it will be sufficiently large in size, they will coagulate or precipitate. That is, they will settle down under the force of gravity. This process is known as coagulation or precipitation. So basically what is happening, now the dispersion phase, dispersion medium, they are separated from each other. That means colloid is no longer stable. Fine. From this picture it is clear. So it is colloid, which is clear, right? Now when we are adding some electrolyte to it, there will be coagulation, because now the small particles, they can come close to each other, so their size will increase, they will be precipitated. So now you can easily decant this clear dispersion medium. So now the dispersion medium and dispersed phase, dP and dm, I have written, both are separated. That means it is no longer colloid. Fine. So after if we can decant this upper clear solution, it will be like this. Okay. Now next we will see what are the different processes by which coagulation is possible. Electrophoresis, that we have already seen when we have discussed electrophoresis, that under the electric field, the colloidal particles, they will move towards a particular electrode. As a result, dispersion medium, dispersion phase, both will be separated, so there will be coagulation. Second method, by heating. That means we are providing thermal energy. So when thermal energy is given towards colloidal particles, what will happen? This thermal energy can overcome the repulsive forces that are present between them, and ultimately they can come close to each other. They will form large particles. Another explanation is, when we are heating it, then desorption of adsorbed ions. We know that in colloidal surface there is presence of some ions, but when we are heating it, these ions, they will be desorbed. That means they will be removed. So now in the surface there is no charge, and as there is no charge, then see, desorption of adsorption ions from the surface of colloidal particle take place. So when there is no charge, they can come close to each other. Another way also we can explain it, that the particles that are present in dispersion medium, their kinetic energy is now increased, so they can also destroy the adsorbed layer. Okay, so the particles of adsorption medium, their kinetic energy is high, so they can also remove these charged particles. Ultimately, what will happen? There will be precipitation, that is settling down in the form of precipitate. Very good example in day-to-day life, common example is egg albumin, that is a protein that is present, that will be precipitated when there is heating, that is coagulation will occur. Third method, mutual coagulation. Mutual coagulation, obviously it means that now we will take two oppositely charged salt and we will mix them in almost equal proportion. So equal proportion is necessary because if it is suppose FeOH3, which is positive salt, arsenic sulfide, which is negative salt. So if we are adding equal proportion, it will completely neutralize each other. But suppose if it is not equal portion, then it will be partially neutralized and partially precipitated. So this is the third method by which we can achieve coagulation. Fourth, persistent dialysis. So in dialysis, what happens? Here only some particles can move through the pores of the membrane. Okay, so if there is presence of electrolyte, obviously for stability of colloid, we know very little amount of electrolyte is added. But if it is very high in amount, then there will be precipitation. But small amount of electrolyte, that is essential for their stability. But if the colloid is subjected to persistent dialysis, what will happen? These traces of electrolyte, they will pass through the membrane in the dialysis process. So now there is no trace of electrolyte, and in absence of electrolyte, there is no charge, so salt will become unstable and there will be precipitation. Fifth method, by addition of electrolyte. We have already seen small amount of electrolyte, it is essential for the stability of colloid. But suppose if the ions of the electrolyte, it is present in excess amount. So if it is added in substantial amount, now the oppositely charged ions of the electrolyte, it will neutralize the charge which is present on the colloidal particles, leading to coagulation. For example, suppose barium chloride is added to negatively charged sol of H2S3. Now in barium chloride, there is both presence of cation Ba2 plus and anion is also present. But as it is negatively charged, that is the sol particles are negatively charged, so here this cation will be responsible to neutralize this negative charge and it will cause coagulation of the salt. Now Ba2 plus is the cation. Suppose we have taken BaCl2, but you may think why not NaCl? Okay, now when it is NaCl, Na plus cation, that will be responsible to neutralize the charge of H2H3. Now one question arises whether NaCl will be better electrolyte to cause coagulation or barium chloride will be better electrolyte, because in this case we have only single positive charge, but here we have double positive charge. So what is the valency of this charge, that matters. Okay, so generally the greater is the valence of the coagulating ion. Coagulating ion means the electrolyte that you are adding for coagulation purpose. You can say coagulating agent or flocculating agent or ion. So greater is the valence of this ion, greater will be its capability to cause coagulation. Okay, so that is why if we compare Ba2 plus, if we compare Ba2 plus cation and Na plus cation, obviously Ba2 plus, because of its higher valency, it will have higher capability compared to NaCl to cause precipitation. Higher capability means compared to NaCl, the BaCl2 that we are adding, amount will be low because this capability is high. So we have to add lesser amount compared to NaCl. So based on this observation, that is greater is the valence, greater is the capability to cause coagulation. Based on this observation, there is Hardy-Schulze rule. From the study of coagulation behavior of different electrolytes, or you can say coagulating agent or flocculating agent or ion towards a particular salt. Okay, Hardy and Schulze, they suggested a general rule. Greater is the valence of oppositely charged ion of the electrolyte. So if the colloid is negatively charged, then we will consider cation. If it is positively charged, we will consider anion of the electrolyte, because in electrolyte we will have both cation and anion. Okay, so greater is the valence of oppositely charged ion of the electrolyte that are added to colloidal solution, faster will be coagulation of the colloidal solution. So we have to check what is the valency of the opposite ion that is present in the electrolyte. So coagulating power of an electrolyte, it is expressed by the term flocculation value. We have two examples. So first, suppose we have negatively charged salt H2H3. So obviously the electrolyte that we will be using, we will focus only on the cation. Now suppose you have used aluminium chloride, barium chloride, sodium chloride. So these are the cations. Now as valency is high, their coagulation power is also high. But when coagulation power is high, flocculation value will be low. Okay, so we will also see what is the definition of flocculation value. But let's see another example, which is for positively charged salt. Ferric hydroxide is positively charged salt. So when we are adding the electrolyte, now we will focus on the anion because it is positively charged. If you look at these anions, we have charge gradually decreasing, 4 minus, 3 minus, 2 minus, minus. So this is the order of the coagulation power. That is, this ion is it has maximum capability to cause coagulation. Now what is flocculation value? The definition is the minimum concentration of an electrolyte in millimoles per liter. As the amount is very small, so that is why millimoles used, not moles. E per liter required to cause precipitation of a salt is known as flocculation value. Fine. So when coagulating power is very high, that means the concentration will be very low. That means flocculation value is also low. So flocculation value, that is actually inversely related to, that is inversely proportional to coagulating power or flocculating power. Okay, so smaller is the quantity needed, higher will be the coagulating power of an ion. So if we compare coagulating power of these three, flocculation value of these three cation, the order will be reverse. Now Na plus will be having maximum flocculation value, then Ba2 plus, then aluminium 3 plus. Okay, here we have some example, that is values of flocculation value. So this is the electrolyte and the colloid is H2H3. This is negatively charged. So obviously we will focus on the flocculating ion, which is scattered. Here flocculating ion is scattered because salt is negatively charged. So here we will focus only on the cation, Na plus, K plus, H plus, Mg2 plus, Ba2 plus, Zn2 plus, Al3 plus. Now see, these three are plus 1 charge. So their values are almost close to each other, though this is a little bit lesser, but they are close to each other. Next, when we are switching to 2 plus, all these are 2 plus, see, their values are decreasing and they are close to each other. And when we are moving to 3 plus, now it is further decreased, and it has to be, because flocculation value, it is inversely related to coagulation power. if it is positively charged, for example ferric hydroxide, now the flocculating ion, it will be anion. So we will focus on the anion. All these three ions are -1. Values are close to each other. These three ions, they are -2. Values are close to each other. It is -3. So value is further less. That is, among all these electrolyte, minimum value is for K3FeCN6 because here the anion is having maximum negative charge. Okay. So coagulating power is inversely related to flocculation value. So it is important to remember because sometimes in question, in the options, different orders will be given and it will be asking whether it is correct order for coagulating power or flocculation value. So you have to read the question carefully because if it is asking the coagulating power order, then and if it is asking flocculation value order, these two will be reversed. Fine. So related problem we have here, as per Hardy-Schulze formulation, that is Hardy-Schulze rule, flocculation value. So here we have to find flocculation value order. Okay, values of the following for ferric hydroxide salt, that is FeOH3. This is positively charged. So see here the table that I have mentioned where positively charged colloids, negatively charged colloids, the examples are given. Then I told that you should remember their nature of charge because here FeOH3 it is mentioned, but it is not mentioned whether it is positively charged or negatively charged. So if you do not know what is the nature of charge, how you will be understanding that which ion of the electrolyte you will choose, cation or anion. But if you know that it is positively charged, obviously you will focus on anion. Okay. So the flocculation value of the following, here we have 5 electrolyte. Flocculation value of the following for FeOH3 salt are in the order. So which order is correct, that we have to find out. Here FeOH3, as we have seen, this is positively charged. So maximum charged salt means it will show maximum flocculation value to negatively charged ions. If you are finding this line confusing, just leave it. It is just remember that as it is positively charged salt, so it requires negatively charged ion. Okay. Now negatively charged ion means we will focus on FeCN6 3-. Why it is 3-? Because you have 3 potassium plus. So obviously the charge will be 3-. K2CrO4. So just focus on CrO4. It is CrO4 2- because you have 2 potassium. 3Cl- because this is 3+. So each chlorine it will have -1 charge. Br it is already -1. This is also -1. Fine. So according to this relation, all these 3 ions are single negative. CrO4 -2. Ferrocyanide, it is ferricyanide because iron is +3. 3 negative charge present. So that means among these 3, in which case valency is maximum? It is 3. So its flocculation value will be minimum because these two are oppositely related to each other and we have to find order for flocculation value, not the order of coagulating power. If it is order of coagulating power, then if K3FeCN6 will have maximum value, but here we have to check the order of flocculation value. So K3FeCN6 ion will be minimum value. So see, efficiency minimum value you can find it in option 2 and 4. Okay, so in option 2 and 4 up to this point it is fine, but see here these 3 are not same, but these 3 all are carrying single negative charge, so they must be same. So that is why option 4 is correct. So all these 3 are same because in each case it is -1 charge for the ion anion, then it is -2, it is -3. Fine. For the coagulation of 150 ml of Sp2H3 sol, 10 ml 1 molar NaCl required. We have to find flocculation value of NaCl. So remember the definition. Flocculation value is the amount of electrolyte in millimoles that are required to 1 liter of the colloidal solution, that is colloidal solution, so as to bring about complete coagulation. Okay, so here first we will find out millimoles of NaCl. How we can do so? Here volume is given in ml and this is molarity. So if you multiply molarity and volume in ml, you will get the corresponding millimole. Next is we have to find total volume, because 115 ml of colloid, but you are also adding 10 ml, so you have to consider this. So as a whole, now the final volume is 125. So 125 ml is basically carrying 10 millimole of NaCl, sorry. So 1000 ml, that means 1 liter. It will contain 10 divided by 125 multiplied by 1000, and this is 80 millimole. So according to the definition, this is the flocculation value for NaCl. Okay, because in 1 liter, this is the number of millimoles that is present. Coagulation of lyophilic sol. We have seen the processes of coagulation for lyophobic sol, but now we will see it for lyophilic sol. Now lyophobic, if we compare stability with respect to lyophilic, obviously lyophobic, their stability is low. Lyophilic is more stable. So here, if we want to coagulate them, that is if we want precipitation, obviously here the amount of that is the process that will follow, that will not be very easy if we compare with if we compare with lyophobic, because they are already unstable. So it is easy to cause coagulation, but lyophilic salts are comparatively stable, so now it will not be so easy. But before discussing what are the processes for lyophilic salt, we have to know that what are the factors that are responsible for their stability. One is charge. Obviously charge, because if there is no charge, there will be no repulsion, they will coagulate. And the solvation of the colloidal particles. So solvation factor is important in case of lyophilic, because they have affinity for the solvent. So that is why solvation is possible. If there is no affinity, solvation is also not possible. That you can see in case of lyophobic, but this is lyophilic, so there will be solvation. So these two are the factors that are responsible for the stability. So if somehow you can remove these factors, you will be able to coagulate the lyophilic salt, that is you will be able to destroy their stability. First we can add electrolyte. Now in this case, excess of electrolyte we have to add, because obviously electrolyte we have also added in case of lyophobic, but the amount here we have to add more, because their stability is very high. So to cause precipitation, obviously higher amount is required. Charged ions of electrolyte removes the charge on salt particles. Neutral salt particles will result, and now these neutral salt particles, as there is no charge, they can come close to each other, they will form aggregated particles to form a precipitate. So any negatively charged salt is coagulated by the cations of the electrolyte, because in electrolyte cation and anion both are present. Okay, and vice versa. Second method is you can do electrophoresis. We have also seen electrophoresis method in case of lyophobic salt, but now also we are doing electrophoresis, but it is prolonged. For a long time we have to do it. So they will be that is under the influence of electric field, salt particle will move to cathode or anode depending on the nature of their charge, and there they will get discharge. Ultimately they will become neutral and they will be settled down because of the force of gravity. So this is the process by which coagulation of lyophilic salt is possible. Protection of colloid. This is actually completely different topic. Okay, so better we will discuss it in the next class. So here we will end with the coagulation. So these two processes are coagulation of lyophilic salt, but we have also seen coagulation process for lyophobic salt. So total 5 points we have discussed here. So we are ending here, that is the coagulation of lyophilic salt.